Ok. Litt nervøs start der, men nå er vi på. Velkommen. Welcome everyone. My name is Helge Penne. I work for a company called Thales, where I do software architecture and development. And I'm going to talk to you today about some things we have learned while trying to make secure software with C++. So, who is Thales Norway? We're part of the Thales group, which is a big French company. We do more or less anything related to security or safety. So that includes aerospace, defense, communications, you name it. Thales Norway is a bit more focused. We're about 200 employees in Oslo and Trondheim, and we specialize in secure communications. And we do some serious work. Our user data, our system assets for some products is user data, which may be classified, and encryption keys. And the would-be attackers for what we make is actually nation states, which sobers you right up. And in C++, well, it sounds barely doable. What saves us is that we do not actually fully trust the software. We can't do that. But still, we want to prevent the attacker from getting a foothold, a foot in the door. Prevent the attacker from getting in and moving further into the system. And the threat model is also a bit difficult. The products will need to communicate externally, which means that we will have software that has attack surfaces. And what we really need is zero exploitable defects, which is, in principle, impossible. The bug count of software, I did some searching for that, and it varies, but it's fairly high. We need to reduce that, and even more important, we need the remaining bugs not to be exploitable. So how do we achieve that? Well, what do other businesses do? An aircraft, for example, is an incredibly complex machine. It has millions of ways to fail. So how can we even dare to fly these things? Well, they build in redundancy. They realize that bugs will happen, but you need to design it, to engineer it in such a way that no single failure will ever cause a disaster. So you build it with two engines, you have two pilots, and so on. And we should strive to do the same for software. No single programming mistake should create an exploit. So how can we do that? Can we devise some redundancy for software that will help us get there? And I structured this by following the path that a bug takes, from making it, authoring the bug, through the review process and release and deployment and so on. So if we can put in some mitigations along this path, several mitigations to try and stop the bug from becoming exploitable, then maybe we can devise something similar. The authoring phase is possibly the biggest one. There are a lot of things we can look at, and I will skim over some of these, and for some I will go in a bit more detail. And it starts out a little bit boring, but we have to go through this as well. Compiler warnings, basic stuff. Enable everything you can. This will find some security-related bugs, initializations that you have missed, things like that. Basic stuff, but you need to do the basics as well. And of course, the warnings must break the build. I assume that you all run with W error, and if you don't, just sneak back home and fix it. Static analysis as well. Clang Tidy, it's free. You should use it. There are commercial tools that you can buy that will find possibly more stuff. We do find that this has some benefits, but in reality, most of the security issues that we find in other ways. Memory bugs, also a bit boring to begin with. You should, of course, avoid the old C APIs for memory and strings. There are other talks about this. I won't go into details. You should use modern C++. You want to use modern C++. So, avoiding the old C stuff is not that difficult. And you need to do tests and use good tooling to detect these problems. There are good tools. The sanitizers are great. Also free. Use them. You need to run this on unit tests, but you also need to test the whole system integrated, which is a bit more difficult. And you need to automate this, put it in your continuous integration pipeline, and do this all the time. And this will catch a lot of stuff. This is really good. So go use those. How many use the sanitizers? Okay, not bad. Could be more. But please try them. They are great. And for modern C++, smart pointers, of course, there are different schools of thought here. Some people love shared pointer and use that for everything. And some people frown upon that. It has extra overhead. And the frowning comes from the second point here. The ownership and lifetimes can get difficult to reason about. If you have an object and you have 10 shared pointers to that, how long does it live? Who actually owns it? Code doesn't show it. But it does prevent use after free, which is good, especially for security. The other alternative is unique pointer. The owner holds it, fine. The semantics are great. You can see who owns it and who doesn't. Problem with that is that if you want to have class B having a dependency on C over there, you can't use unique pointer. So you have to use some other way. And we tend to resort to normal pointers as references, which makes it possible for use after free bugs to creep in. So it's not ideal. I sometimes wish there was a third way, where you could solve this as well in a secure way. But it doesn't exist. You could try to mimic this with shared pointer and weak pointer, but that kind of mixes this up semantically with this normal use of shared pointers, which will confuse things. So I'm not sure if we have a great solution for that at the moment. You could make your own classes for this. It's not a bad idea. There's a good talk by Sean Parent at C++ Now this spring, which talks about memory safety, among other things. And it's really worth a look. It's good. His conclusion is that value semantics is the only safe alternative. Incidentally, this is also the direction that the Rust borrow checker will push you in, if you try that way. It also sort of rhymes with what Robert Secord said this morning. C++ will never be memory safe, unfortunately. So you just have to do the best you can. Taking a step back, we do protocols a lot. Where do the vulnerabilities in protocols come from? Well, probably you're reading or writing outside your buffer. So maybe your argument to the subscript operator is out of range. Or similarly for pointer arithmetic. I do not recommend pointer arithmetic, by the way. Please don't. Why does this happen? Well, maybe you have an attacker that sends you an input that causes integer overflow, and then you use the bad result as an index. So overflow is a really important issue. And in my opinion, C++ and C integers are fundamentally broken. Expressions promote to int are unsigned, even though you don't ask for it. And when you use the result, it gets converted back to smaller types silently, and it gets truncated if it needs to, changes the value, and also overflow is silent. And nothing about this is secure. It was a reasonable design choice at the time, in the 70s, but that's a long time ago. There were no attackers. There were no hackers at that time. It doesn't fit well nowadays. So what do? Well, we can try and fix some of the conversion problems. Yeah, let's see if the code examples work. This is just a primitive, simple program. Here we go. Oh, that was a bit small. Anyway, can you read that? Good. It creates an 8-bit integer, and then it inverts the bits. Simple enough. Let's see. Now, if we run that, you would think that this would output 33 hex, but it doesn't. It inverts also the extra bits that you get because it's promoted to int. So a bit confusing. And then when you convert back to small types, it truncates. There are some good warnings you can enable for that, which means that every time this happens, you get a warning. And because the warnings break your build, then you need to do something. You need an explicit cast. For explicit casts, we use static cast, but that just suppresses the problem again. So what you actually need to do is to implement your own cast, which will trap any conversions that cause bits to be thrown away. That makes it a lot safer. There is nothing like that in the standard library, but it's easy to build. And also, even worse, this is a bit subtle. You don't see this every day, but make shared is broken in this way because your constructor will be called inside the implementation of these functions, and all warnings are disabled in the standard libraries. No warnings at all. They can do anything they want. It just compiles, which is a bit concerning. Let me show you that. So, simple. Oh, sorry, wrong window again. I'm not sure how to fix that. Anyway, simple class takes an 8-bit int in the constructor and then puts that in a variable. And I initialize that using unique pointer. I have the warnings enabled, and the compiler gives me a nice error output. But if I use the second line instead and use make unique, then no, compiles just fine. And the output is wrong. No warnings. Which doesn't go well with security. So you actually need to write your own replacement functions if you want to fix this. It's the only way. It's simple, but it's a bit annoying. Same goes for in place back. It's also broken. You can't fix that because that's a member function. But you don't really need in place back very often. It's the optimizer will make pushback just as efficient in many cases. And then there's a bigger problem, the overflow. Unsigned integer overflow is allowed, just silently wraps, which is not very secure. Signed integer overflow is undefined behavior, which is worse. If you have a program that needs to be secure, then you cannot have any undefined behavior anywhere. So, do pull requests help this? Nah, not much. The errors are subtle, they're hard to spot. We've had several bugs that we have found through other means that passed review that were security critical. Problem is that the abstractions get in the way. The way you reason about expressions, well, when you do that mentally, you think in perfect numbers. It's very hard to think in terms of what the compiler will do. You're not trained to do that. And also overflow issues are incredibly complex. Robert Sequat's book, which you should read, it's very good. He spends 84 pages on integer security. Reasoning about this, if it's a simple addition, is doable. But once you get into more complex expressions with multiplications and such, it's incredibly complex. A hypothetical example, this is just a function that tries to receive a packet of data and decode the payload. So there's a header and a payload. So the header has a length field, and the code tries to see if the packet is big enough. Is there a payload after the header? So it just takes the length field, subtracts the header size, and checks if that is bigger than the required size for the payload. And if it is, then it returns a deserialized payload. Problem with this is that the length field is probably unsigned, and if the attacker sends you a header with a length that is smaller than the header size, then this underflows. And it becomes very large. So it's always true. And you try to deserialize data that isn't there, and you get a buffer. Well, you read outside your buffer, and you have a security vulnerability. But the equation looks just fine, the way you're trained to think about this, because you think in perfect numbers. You could fix this by just moving the header size to the other side of the equation, and you don't have a subtraction anymore. But these things are hard to spot. So in a way, the language is the problem. And the inability to detect overflow is terrible for security. And also the implicit conversion and truncation. And this is from a time before hackers. I'm not accusing anyone of doing a bad job here. It's just that the time has passed and the situation is different. So what do you do? Well, you have to fuzz test everything, all your attack surfaces. How many people use fuzzers? Oh, that's not many. Good for those who do. If you have software that needs to be secure, you need to fuzz things. The tests will find some bugs, but the fuzzers will find much more. I can't go into detail on this, but there are great talks about fuzzing, and if you write software that could be attacked, then you absolutely need to do this. And you also need to test the coverage. Does the fuzzer actually exercise all the code? It's an incredibly powerful tool, and I strongly recommend that you do this. But it would be better if we could actually find some of these bugs. Chandler Carruth had a talk a while ago where he recommended using signed integers for everything. It's on YouTube. You can have a look at it. His argument was that the edge cases are further away. You typically use numbers that are small and around 0, and the feeling was that it was dangerous because 0 was the edge case. This puts the edge cases as far away from 0 as possible. And then the undefined behavior sanitizer could detect any overflows. This is what Robert Seacott was ranting about in his talk last year. There are some problems with this. You introduce undefined behavior in the code, which is bad. You don't want that if it's supposed to be secure. You don't want that in any case. And also, semantically, signed ints are often a poor representation of the domain. The length of a vector will never be negative. The big problems is that the edge cases are further away, because you are more likely to forget to test them. But the attacker will test them, because he knows what to look for. And also, it muddies the waters, because many of your expressions will be unsigned anyway. You start with the length of a vector and you do some arithmetic on it. That's still unsigned. So this is not pure. And then Robert Seacott had this talk last year where he says you should prefer unsigned integers, especially when it fits the problem at hand. And then you test with a sanitizer, because the undefined behavior sanitizer has also tests for unsigned integer overflow, even though that's not undefined behavior. This is not well known. Challenges with this will detect intended overflow as well. And even some of the standard libraries do this. So you will need some suppressions. Surprisingly few, so this is perfectly doable. And now, of course, the normal caveat, testing is never perfect. But this is an interesting technique. I really like this one. So how well does this work? For GCC, well, unsigned integer overflow checking is not implemented. And there are some problems with detecting signed integer overflow as well. Let's see. Now it opens in the right place. Good. So this is a simple program that creates a variable b, which has the maximum size for a signed int. And then we add 1 to it, so it overflows, which is ub. And then we test it, and it returns 1 or 0, 1 or 2. This one returned 2. It's compiled with the sanitizer on to detect this, but it didn't. It ran anyway, which is bad. Let's see. But this is compiled with optimizations. And if I turn those off, it detects the error correctly. So GCC concludes that there is undefined behavior. It runs it through the optimizer, and it exploits the undefined behavior to do whatever it wants, and then it instruments it with the sanitizer, which is too late because it's not detected. So this doesn't work at all. For Clang, well, that works as expected. And it gets trapped even with optimizations on. So this is great. This works really well. And there's a special sanitizer mode that's just called integer that catches everything. Signed, unsigned, truncation, all of it. So you need to use Clang if you want to do this. You can't use GCC. Other solutions. There's a library called Boost Safe Numerics, which is really interesting. He defines integer classes and all the operations on them, and it will trap at runtime any of these problems. So it fixes the root cause. Of course, increases compile and runtime a bit, and your code will look slightly different. I haven't tried this, but it looks really interesting if you want. Or you could use Rust. Fixes all that. Rust has this under control. But sometimes you have to stay in C++ for various reasons. Another security issue, which is really important, is data races. I kind of like this one. This is a picture from Mozilla's offices. And someone put a poster up and says, you have to be this tall to write multi-threaded code. And as you can see, he doesn't qualify. He's too short. We all are. There is a sanitizer for this as well, a thread sanitizer. Really, really good. It's excellent. It's always right. When you run it, you sometimes think, well, this is a false positive. My code is correct. And then you stare at your code for 15, 20 minutes, and you realize that, no, the code is broken. We all suck at writing multi-threaded code. I do. The thread sanitizer has proven that I do. And I think you all probably do as well. How many use the thread sanitizer? Okay. Then you probably know what I'm talking about. The task is simply too difficult. But run the thread sanitizer. Run the thread sanitizer. It's great. On the complete application, good test scenarios. Again, you need to have good coverage. It only detects data races that actually occur. So there are bugs that will manifest themselves with a low probability. So you have to run it for a long time. You have to run it on all your pushes and on all your long-term tests. Run it every night. Run it on all changes. Put it in your CI pipeline. What we've learned is that the note on the wall should be higher up. And you need to fix this in your architecture. You need to devise an architecture that avoids using basic primitives like threads and mutexes in code that you write on a daily basis. Actors are good. Active objects are similar. That makes the problem a little bit easier. So no basic primitives. This is hard sometimes, but the basics are not good enough abstractions. So to summarize the authoring part, what you end up with is a monster pipeline in your continuous integration system. You need to run with a large number of sanitizers on your unit tests, on an automated full system test, and on Fuzz tests. And also, the optimization level matters due to UB. As we saw with GCC, 0, 02 made a difference. So you need to run this also both on debug and release. And you need fuzzers for all your attack surfaces. So this is a big investment, but it really pays off. So if we write a bug, what happens in the review process? I strongly recommend you use pull requests. Most of you probably do. You need to promote a good review culture where you don't argue about formatting. Leave that to Clang format or other tools. And you need to focus on the important stuff, the design and the logic. I also recommend that you use your CI system to generate coverage reports so that you can check, has this code that I'm reviewing actually been tested? But what we find is that the pull requests do not actually find many security bugs, unfortunately. But you should still do that for other reasons. If a bug passes review and makes it into the main branch in your Git system, what can we do to stop it there? Well, the fuzzing is important here. You should do cumulative fuzzing. What you can do with the fuzzers is that you can start them out with some good seeds. Then you have the CI system fuzz for hours every night when nothing else happens. And then when that's done, you can keep the state and use that when you continue again tomorrow. And that will accumulate years of runtime for the fuzzers, which they sometimes need in order to dig down into your code in a good way. And again, coverage data is important. You need to be able to verify that your fuzzer has actually tested all the important code and all the important paths. And some of them will be hard to reach. If you do this on a protocol, and the protocol has checksums, well, the fuzzer can't guess the correct checksum, so you need to help it a bit. And if the protocol has states, you will also need to create fuzzers for each and every state in order to be able to test the logic in each state. So it's a bit of work, but it really pays off. And do not forget your third-party code. Fuzzers can actually be a problem here, because if the attacker can guess what third-party code you're using, then the attacker can fuzz that code, find the vulnerabilities, and use those to attack you. So if you have third-party code, someone needs to fuzz that, either the person who wrote it or you. Now, what if the bug is activated? Can we do something at that stage? Well, because some bugs will slip through and be released. The systems that we make are usually simple in the sense that bugs that terminate are not exploitable. So a safe program is a dead program. If it doesn't run, it can't have any security issues. But not everybody has that luxury. So what we can do is to try to trap these at runtime. And for that, we need to talk about Asserts. Okay. Assert is great. You should definitely use this. Use it to check function parameters, use it to check other invariants. But it only affects debug builds. I guess most of you have used or do use Assert in some way. So what about release builds? Well, your program is, in a sense, a massive finite state machine. And the code that you write your code based on the assumption that your invariants hold, that your asserts pass. Your asserts just state the assumptions you have made when you write the logic. If the asserts do not hold, then you are in a state that you haven't modeled. You're in a rogue state. Anything can happen. Your whole program is UB. There is some good literature on this. They call it the weird machine. You could check that out. It's interesting. And the end conclusion is that if your assumptions do not hold, then your program cannot be allowed to continue, because it can't be trusted anymore. So you cannot disable asserts in your release builds. It's not safe. And for that, you just need to define your own macro that also affects release builds. You terminate in debug as normal, and in release, you take the action appropriate for your application. Terminate or go to some safe state. It depends. I would not recommend just undefining ndebug. You could do that, but there may be other code that depend on this being used in the normal way. So don't change its semantics. The other thing we can look at is the subscript operator. And this is where I'll go into a little bit of a rant mode, maybe. Integer under overflow bugs will happen unless you run the sanitizer in release as well. I'll get back to that. And we need some redundancy, some defense in depth. Basically, you have two alternatives. You can use the subscript operator, but that is undefined behavior if you go out of bounds. And then there is the at function, which hardly anybody uses. This will throw if you go out of bounds. But we all tend to use the subscript operator. Now, why do we do that? Well, is it because of the need for speed? Well, no, actually, I don't think so. It's a premature optimization. And if we look at that, let's see. This is a simple program that just sums up the values of some integers. Let's see. If we go over here, you'll see that it generates a little bit of code. It stops at 3e. And this uses the subscript operator, as we usually do. Now, if I change that to use the at function, what happens? Nothing. It's the same. Where did the bounce checking go? It's gone. This is compiled at 02. No, 01, sorry. So what happens here is that the optimizer looks at this and thinks, well, you cannot go out of bounds here. So it can all be optimized away. It's the same code, which is a bit surprising. So using the subscript operator is a premature optimization in this case. The optimizer will figure out that this is safe and just remove that. So you only pay for the bounce checking if your code is insecure, in a sense. It's simplifying it, but it happens a lot. So that's probably not a valid reason. And then some people say, well, user error. You should ensure that the index is correct. That's a no. That's naive. That's error prone, because you will write bugs. Doesn't matter how clever you are. Bugs will happen. I think we use it because it's pretty and it's compact and the code looks nice. And we need to stop doing that. And all this happens because the priorities of the language are outdated, in terms of security at least. Speed is always the default, and security is opted in. And the nice API is unsafe. And the safe API is unattractive or even missing. For vector, the subscript operator is unsafe, and at throws, but it looks kind of ugly, so we don't use it. Optional is the same. And then the really ugly stuff, span, has a subscript operator, and at does not even exist. There is no safe way to use span. Nothing. It was proposed in 2018, and it got voted out. The committee said no. Didn't like it. So security was not a priority in 2018. There is some new hope. It's proposed again. I hope it goes through. But it shows that the priorities are wrong. And in my opinion, security should be the default, and speed should be opt-in nowadays. We need to change this. And the optimizer can still get you the speed. Look at Rust. It has bounce checking, and it's still fast. And C++ has got this wrong, and things are not changing fast enough, in my opinion. Now, we can actually fix this. All these unsafe operators could trap by default, because out-of-bounds access is UB, and UB allows anything, also bounce checking. So it would be backwards compatible. It would not break anything that isn't already broken. And the optimizer will remove the overhead most of the time. And we could make some functions for those who still want to be unsafe, clearly marked as such. This will not be popular. Yeah, you laugh. I can understand that. It will be very unpopular. It will be thrown out at the first vote, but it would make C++ a lot safer. So while we wait, you could use a coding standard. I assume many of you have one, and discourage these unsafe operators. You could prohibit span. I would recommend that you do that. It won't be popular, I think, because your code will look uglier, but it will be safer. There are also some other interesting ways to fix this. You could use the debug version of the standard library. How many people know about that? Yeah, not many. This has bounds checking. You can use that. But it changes the object layout, so you need to compile everything, including the standard library itself, with this flag, which is a bit of work. So I don't think many people do that. But there is some other stuff you can do. There is a switch that you can turn on that gives you bounds checking. It does not change the object layout, and you can also use it in release builds. And this works. And when I found that, I thought, well, great. And then I also got deeply frustrated. Why is this not on in debug mode? This could be turned on by default, but it's not, because speed is a priority also in debug mode. Go figure. I can't understand that. So this is an easy win. If you want to remember one thing from this talk, I think it should be this. Go home and turn it on. That's for GCC. If you use Clang, it has a different name, but it does the same thing. This gives you bounds checking at a low cost, and you just have to turn it on in your makefiles. So what about the overflows? Well, you could actually deploy the sanitizer in your release build and fix it. You will need some suppressions. Some of the standard libraries will cause overflows by design. A crypto library will do this all the time. Basic string does this. So some suppressions are required. The random libraries do this. But surprisingly few suppressions are required. So this is easy to set up. This will give you internet security on par with Rust or Ada or whatever. There are also some compiler options you should look into. ASLR, stack protector, so on. I will not go into detail about that here, but there's a lot of good literature out there that you could look at. This also changes from time to time. And do not forget architecture-specific protections. If you control the platform, if you have a Linux distribution of some sort that you have configured, make sure that the stack is non-executable. If you are on very new ARM platforms, there's a really cool switch that you can use, which is called branch protection. The newer Macs support this. This actually adds some extra instructions to the functions in your program that sign the return value cryptographically and then check the signature on return. So if someone tries to do return-oriented programming and jump into your functions towards the end to use it as a gadget, the program will trap. So this protects against return-oriented programming, which is really cool. I think Patricia Aas is holding a talk later about that technique, return-oriented programming. I'll go see it. I think maybe you should too. Of course, someone has already demonstrated a successful attack against this, but I'm not sure how practical it is. Finally, if an attacker is able to trigger a bug and get in, is there something more you can do? Yes. This is not a topic of this talk, really. It's something somebody could talk for hours about, I think, but it's outside the scope. But try to ensure that there is nothing of value to find. Sounds strange, but do not put your high-value asset in the first process that the attacker breaks into. So if you have, say, a password file that you don't want to leak to the internet, put that somewhere else, somewhere deeper inside your system. If you look at what banks do, they tend to put their highest value targets inside dedicated hardware. You could go read about that, hardware security modules. If you can't use or afford one of those, you can build something almost as good in software if you put your mind to it, which is an interesting technique. All right, so where does all this leave us? Well, the good part, you can detect integer overflow at runtime, even in releases. You can get bounce checking if you want to, and you should. So you can have reasonable redundant protection against buffer overruns. And there is lots of good tooling that you should invest in. The bad, memory errors, still possible, and will always be possible. And the ugly part, data races, complex, problematic. I don't think they can ever fix that. And the sad part, I think security needs to become more of a priority in the language. Okay, I spoke a little faster than I planned, so I'm ahead of time. Questions? Yes.
Okay, I can judge.
There is one here. Does it work?
Oh. Okay. Thank you. Okay, it works. So thank you for the talk, and I have a question about square brackets and add operator for vector. Do you think if we use high-level abstractions, say ranges library, would it improve the situation in general? So the point is, in modern C++, you probably don't really need to use both of them, like neither square brackets operator nor add operator. It's either what you use, it's either range-based for or ranges library, which is pretty much the same as .iter in Rust. Yeah, that was the question.
Yes, yeah, you're right. You should avoid it if you can. But I still see new code written with this, so it's hard to avoid at all times. But yes, if you can avoid using the square brackets operator or the add function, then that is even better. Absolutely.
Yeah, thank you.
Yes, at the back.
Thank you for a good talk. And we were wondering about fuzzing, how to get started. What have you experienced that we can avoid experiencing?
Ooh. Getting started is not that difficult. You need to set up the infrastructure. You start out by doing it locally. And making a fuzzer is not that difficult. You have to write a small function that takes some seemingly random input and just puts that into your API. And then you build the fuzzer and you run it. But we have seen that you absolutely need to use coverage data in order to see what the fuzzer does. And to give it a good start, you also need to provide some seeds. So it will eventually generate good test vectors on its own. But if you can give it a good starting point, if you can give it a dozen inputs that are actually valid and good and a bit different, then it will cover a lot more of your code very much quicker. So some good seeds and coverage. It's a good place to start.
Thank you. And you have made it internally, the fuzzer?
No. This is a part of at least of Clang. I don't remember if it's part of GCC. Okay, well, I have a colleague here who's better at much of this than me, and he also provided some of the examples, Jon Efteland, so thank you for that. So it's free and it's easy to start using. There was one talk I saw about fuzzing where they joked that you find 20% of your bugs with tests and 80% with fuzzing. So there is some truth to that. The really, really ugly bugs are found by fuzzing. We have had bugs where we look at it and And we think, well, how on earth did the fuzzer get there? How did it even find that code? It shouldn't be able to reach that, but it still did. Yes.
Thank you for the talk. I have a question regarding STD span. I understand like the STD span was originally what like you is a new safe tool, use it, and then it didn't become it. Yes.
I'm sorry, I didn't catch all of that.
Yeah. You said the ban STD span. Yes. Don't use STD span.
Yes.
Yes. And but the STD span's supposed to be that safe tool that people should use. Yes. But my question is maybe there is a guideline support library and which has actually a bounce check span.
Yes.
So you would prefer to use that one, I would say.
Yes. To moderate that a bit, if you don't use the square bracket operator or at, then fine, go ahead and use span. But if you find that you have to use the square brackets, the subscript operator, then that's dangerous. If you use ranges or range-based for loops, then it works great.
Maybe just to follow up a question, would you encourage people to write the Kalang tidy checks to actually verify that you don't use something? Because one thing is to ban, yes, you say it, but then it's human control then. I mean, manual, it's not cool.
Right. You're talking about writing your own Clang tidy checks.
Yes.
That's a cool technique. I haven't done that myself, but it looks really cool. Is it difficult?
Not that much.
Okay.
Yes.
Yeah, that would be a really good idea. And probably a bit of fun as well. Okay. Other things? Yes.
Are there any good libraries, security libraries? So, for instance, let's say you have a vector, you have a vector class which is safe, which it has built-in bounce checking on the square operator.
Yeah, you could use that, but you can get bounce checking with the standard one as well. So I would probably just use that. Just turn it on with the compile switch. Yeah, but if you have one and like it, then sure, go ahead. Yes?
I have been using HSMs in the past, actually from Thales, but do you know what is the performance if somebody is able to do that?
The performance compared to
standard processor on servers or something. So is there what are the performance penalties actually?
Okay, so the question is, what's the performance of an HSM compared to running this in a process on a server? I don't know. I would expect that because the HSM is something that you have to communicate with externally, that maybe it's a bit slower. It will get you much better security. But you can emulate some of that security in a process if you isolate it well, if it has a very narrow API and you check it extremely well. There are also some interesting techniques on servers like Intel SGX, which provides some extra protection, extra isolation that you could look into. Also, HSMs are expensive.
Yeah.
So that was an extreme example.
Yeah, thanks.
Yeah. It was more to illustrate the importance of hiding your assets.
We have been also doing few weeks. I don't remember. I have never tested it in high.
Okay. Yes. Anything else? All right. Thanks a lot.